I'm showing you the derivation of addition subtraction formulas. So before you getting into the first part, you should have some knowledge of a higher view knowledge of what we are trying to achieve here. With this picture, if you think about the red curve and the green curve, if when we add two sine curves or there are phase changes between the red curve and the green curve, and there are slight amplitude changes as well. So amplitude is the vertical height of the curve from zero, and phase change translates it to the left and right. So adding two sine curves or cosine curves will end up with another sine curve. And what we are basically going to look at is what phase changes do we need, and what of those here added together that will help us get another sine or cosine curve. Now, I use sine and cosine interchangeably because they're simply the same curve trans 90 degrees. So we are looking at what the result of a double formula what's the results of having two angles added together, and that would simply leave us with another scale factor multiplied by its cosine curve. So we'll have some of the value here, and we will, by the end of this chapter, come across uh, uh, why these derivations are used to help us solve engineering problems and as such. Encourage my students to follow with me whenever I teach this section of the course. You can download the Word version or the PDF version of this section and label the sides of the square rectangle here with me, because it will help you understand how and how the formula is driven, and that should help you consolidate the understanding of the derivation of this formula. So the basics trigonometry is written for you in this red box on top left, top right corner. Sine of theta is opposite over hypotenuse. Therefore, whenever we have opposite side, we want to calculate opposite side of a right angle triangle, we take the hypotenuse and multiply it by sine of the angle. And whenever we want to calculate adjacent side of the right angle, we can multiply the hypotenuse by cos of the angle adjacent to that side. So these uh, terms I'm underlining here on the top right, we will use them again and again in this derivation. So looking at the rectangle here, we've got this angle alpha here, and we have another right angle triangle inside that rectangle with a hypotenuse of 1. So right off the bat, we can see that this length A to C has a hypotenuse of inside. Therefore, we can call this as uh, cos of angle inside this triangle is beta, and that multiplied by the hypotenuse, multiplying by 1, will leave it as it is, cos of theta, cos of beta. So that is one of the sides, and this side of the triangle is the opposite side, and we can label that as sine of beta, because sine of beta multiplied by 1 leaves it as sine of beta. Now this angle here leaves this angle to be 90 minus alpha, and that means that angle ECF is also alpha degrees, because we're dealing with a rectangle here, and therefore the of uh, is adjacent of the triangle with alpha degrees. Therefore, we multiply cos of alpha with the hypotenuse, which is simply sine of beta. Sine of beta is the hypotenuse, and we multiply it by cos alpha. So that's the length C to F. We calculate, going back down to the bottom triangle here, the length B to C is the opposite side of angle alpha, and opposite is relates to the sine. We're going to take sine of alpha and multiply it by the hypotenuse, which is cos beta. So the length B to C is simply sine alpha times cos beta. And the length A to B is the adjacent side of the triangle. So we're going to take cos alpha and multiply it by the hypotenuse, which is cos beta, right? So there's only one more side that we need to calculate here, and that is E to F. E to F is opposite side of the angle alpha. Opposite relates to sine. So sine of alpha multiplied by the hypotenuse, which in this triangle CEF is sine beta. So then E to F is simply sine alpha multiplied with sine beta. Now here we have all the ingredients we need for the derivation of our answer, which I'll show you uh, here. Actually, we know, going back to the basics of I'll change my color. We have angle alpha plus beta here. Okay, so the angle EAB is alpha plus beta. Now, the bottom of this rectangle, this side, top of the rectangle, therefore, these two parallel lines tell us that there is a alternate angle here, and this angle GEA is simply alpha plus beta. Okay, so this alpha plus beta there, and this right angle triangle AGE has angle alpha plus beta there, and its hypotenuse is also 1. So what can we call this length A to G? Think about it, pause the video, you can tell me, and I'm going to give you the answer now. The answer here is sine of alpha plus beta, because simply this is the opposite side of the triangle. Multiplying that by 1 will leave us with what it is already, sine of alpha plus beta. And at the same time, call this length G to E. G to E, the adjacent side of the triangle AGE, adjacent to this angle here. Therefore, we can call it cos of alpha plus beta. And that multiplied by 1, the hypotenuse of the triangle, will leave it as it is. Okay, so now we have almost all the ingredients we need for the derivation of the formula. Okay, so what we want to know is, we can start with plus beta. This length here, length G to E, in terms of the lengths I've labeled, what can we say it is? We know that G to E plus E to F must equal to A to B. Therefore, we can say that if we subtract EF from A to B, we will have cos of alpha plus beta. So A to B, take away EF. Okay, what's A to B? A to B is cos alpha multiplied by cos beta. We are subtracting sine alpha by sine beta. Okay, so that's the derivation of this addition of angles. And if I change my pen back to another color, so what is the sine of alpha plus beta? That length there is equals to length, so A to G equals to length BC. Therefore, what is BC is alpha cos beta. What's C2F? C2F is cos alpha sine beta. So that's the derivation of this double angle formulas. Now here we have done the addition. I suggest you pause the video and have a go at the subtraction formula, and next video to show that. In this part of the video, I'll show you the derivation of the subtraction formulas. It is almost similar to the previous example, but here I've changed the angle and labeled alpha to be angle GAC. So, and angle uh, EAC is beta. So the red angle here, small angle beta there. If we subtract beta from alpha, we end up with the blue angle GAE, which is alpha minus beta. Okay, so ultimately we want to know what's the opposite side to alpha minus beta, because the hypotenuse there is 1. Uh, this side of the triangle will be sine of alpha minus beta, that is G to E, and the adjacent side of that is cos of alpha minus beta. Okay, so we're gonna find the ingredients uh, on the right side of this shape here. So first of all, the the angle ACB is alternate angle with alpha. So this angle is alpha here. That means that in this part of the this angle here is 90 minus alpha, and that leaves this angle to be alpha here, and that means this angle here is alpha. Okay, so when we start uh, finding the length A to C, A to C is beta, and that is the adjacent side of the triangle AEC. So we're going to call it cos of beta multiplied by 1. We'll leave it as it is. So A to C is cos beta, length E to C is sine of beta. Okay, so that's this length here. Length to E is, well, that's opposite side of angle alpha. Therefore, I'm going to call it sine of alpha multiplied by the hypotenuse, which is sine beta. And the angle, well, that's sine C to F, is adjacent to angle alpha. Therefore, I'm going to call it cos of alpha multiplied by a hypotenuse, which is sine beta. And now coming down here, B to C is adjacent to angle alpha here. Therefore, I call it cos of alpha multiplied by hypotenuse, which is cos beta. Finally, length A to B is opposite side of alpha, so we call it sine alpha multiplied by hypotenuse, which is cos beta. Now we have the ingredients we need for the derivation of the formula. Call length cos alpha minus beta, that's length A to G equals to length F to C. So this is A to G here, and that's F to C plus E. So that means we are adding sine alpha, sine beta, adding that to cos alpha. Okay, so that's one of the formulas we need. I write the other here. The this length g to e. So g to e is sine of alpha minus beta, which is equals to is a to b subtracted by e to f. Length a to b is sine alpha cos beta. E to f is cos alpha sine beta. So that is it really. So these are the famous identities. You may be asked to prove them. There is a question in the book that you have to prove them, but in general, I've got good news for you. You can find these formulas in the A-level formula booklets. Okay, I'll see you in the next video. I've got there is 10 version of at which we can drive from sine and cos that we already find out. So 10 of uh, we were asked to prove and show why is it that it's in this formula. So you can use the fact that tan is sine over cos and rewrite the right hand side as plus b over cos of a plus b. Now, using the formulas that we I've put on top of the page, we can rewrite that as sine a cos of b and so on. That's just using the formulas that we derived in the previous part of the video. And this is not quite simplifiable yet, but we can divide each and every term by cos A by cos B. Now that's one of these denominators. So this part of the denominator, I'm saying repeat and take it and divide every term by every other term by cos A cos B. So we'll get some nice simplifications. I can see in the denominator this will become a 1 and this becomes tan A tan B. If I take that and write cos A cos B in a way, and again I'm dividing this by cos A and cos B, so I rewrite the numerator here. We will have tan of A plus these two coses cancel away, so we will be left with tan of b in the numerator, and we said the denominator already simplified to 1 minus tan a multiplied by tan b. Okay, so there is the addition formula for tan. I'll drive the subtraction in the next part of the video. This part of the this formula is similar. We're gonna turn right hand side of this equation and use sine over cos instead of tan. So we'll have such expression, and using the definition of double subtraction formulas on top of the page for sine, we can replace the numerator and denominator by these expressions. And again, we're going to divide each and every term of this fraction by cos A cos B. So I'm taking every term and dividing every term by cos A cos B. We have cos B here. We will have that. Actually, gonna keep things nice and tidy here and show. So we will have this expression where the denominator, every term here cancels away nice and neatly and gives us a 1 in the denominator there. Then we'll have these two will give us a tan of A, and sine over cos b will give us tan of b there. Is multiplication between those two tan functions. Then in the numerator we'll have tan of a. This cos b and cos b cancel, cos a and cos a cancel. So basically we're left with tan of a subtracting tan of b from that. So I'll see you in the next example. This is the formula for tan of a minus b. You will find this formula in the formula booklet as well. So let's look at the next example. We are asked to prove this identity, and we can start from the left hand side, and if you want to add or subtract two fractions, you do need a common denominator. So that means that we have to cross multiply fraction multiplied by cos b. So cos a here will multiply by cos b, and in the denominator we'll have sine b divided by cos b. And I'm not going to repeat the denominator. For the numerator of left hand side we will have sine a multiplied by sine a multiplied by sine b. From expression you should be able to recognize that when you have subtraction of cos a, this subtraction actually turns out to be addition. That is the definition of a plus b there. So that's just checking your knowledge there over sine cos b. Okay. So that's that example there. Let's look at the next example. So let's understand this problem. In this last example, we've been given an equation 2 sine x plus y equals to 3 cos x minus y, and we have been asked to express tan of x in terms of tan of y. So looking at this equation, there is no tan here, and you maybe divide sine by cos and think that that's going to give you tan, but unfortunately, because of the differences in the input angles, what's in the bracket for sine and cos is not the same. Therefore, that does not simplify to tan of tan of x minus y at all. So we're gonna have to use our trigonometric that's I've put on top of the page here, sine of x plus y. We're gonna expand that and write it as such, and write cos with the same formula. We use the subtraction of the angles, and cos tends to have actually turned into a plus there. We're leaving the coefficients of 2 and 3 at the front of each bracket here, and what we can see here that we turned one complicated equation into another complicated equation. So what do we do? Where do we go from here? Okay, so as always, there is something that's special about cos x, cos y. We're going to take each and every term here and divide by cos x, cos y, because that turns out to make this term into tan. Okay, so I'm saying that we're going to divide each and every term here by cos x, cos y. So this term will become a 1 inside the bracket. This term here will become a tan of x, and cos y here will turn this into tan of y, and similarly to tan x and this cos y here, cos x here will cancel away these two and leave tan of y here. We will have 2 tan x here. These two cancelled away, cos x cancelled away. We left with tan of y here. Over here we'll have thing here cancels away to 1, and here we will have tan of x multiplied by tan of y. So now we can multiply the brackets here, and just thinking back to our purpose, the purpose is to extract tan of x. So we'll have 2 tan of x here and 2 tan of y. We can think about multiplying out and adding and subtracting all the terms that have tan of x's in them. So I see tan of x here and tan of x. So let's get those two on one side of the equation. I'm going to leave tan of x here and subtract 3 tan x. And unfortunately that tan y comes along with it because it's a product. And on the right hand side we'll have 3 take away 2 tan of y here. And the purpose is to tan of x here, so I'm factorizing it. Out of the left hand side we'll have 2 take away 3 tan y here on the left, and we close that second bracket, and we don't have to factorize anything on the right hand side. There is no tan of x here. So final step of this equation is to divide both sides by this bracket, 2 minus 3y. So I'm going to keep the right hand side as it is on top of the fraction and have the denominator to be 2 take away 3 and y. Okay, so happy practicing with exercise 7a. I'll see you in the next video.